Hello, hello. Today we're going to look at Chapter 7, Lecture 17, Learning Objectives 4 and 5. We're going to look at ionization energy and electron affinity in this video. So ionization energy is the minimum energy required to remove an electron from a ground state gaseous atom or ion. So when we talked about the work function, this is what we're talking about. And this energy is going to be absorbed by the atom. And of course, we can remove it from either an atom or an ion. You can remove electrons from an ion to produce a +2 or +3 charged ion. And of course, the energy depends on what type of electron you're trying to move, whether it's core or valence, or whether the substance is charged. It also depends on our effective nuclear charge. So all of these will affect how hard it is to remove an electron. We have what's called the first ionization energy, and that's when we're removing our first electron. So this is the energy to remove the first electron. Then, of course, the second ionization energy is going to be removing an electron from a +1 ion. So I'm just going to put big I, big E for ionization energy. Or energy to remove an electron from a +1 cation. And it's going to be harder and harder to remove electrons as you've already removed one. So it is harder to remove an electron from a +1 cation versus a neutral atom. So we'd say that successive electron removals are or require more energy. Okay. So our first one is always going to be our lowest out of all the ionization energies. And then if you remove an electron that is a valence electron, the ionization energy is not going to be that significant. But if you try and remove an inner shell electron, it goes up significantly. So inner shell electrons or inner core electrons, or core electrons, inner shell electrons take a significantly larger amount to remove amount of energy to remove versus a valence electron. So these are just going to be much harder. For instance, sodium, neutral sodium, its first ionization energy, I1, is equal to 496 kilojoules per mole. Its I2, where we're removing a core electron, is 4,562 kilojoules per mole. So this is removing a core electron. So it is always significantly harder to remove a core electron than a valence electron. And then as we go down our periodic table, going from sodium to magnesium to aluminum to silicon, so on and so forth, as our Z effective increases, so does the ionization energy. So going from sodium to magnesium to aluminum to silicon, phosphorus, sulfur, chlorine, and argon. In general, our Z effective is going to increase, so our ionization 1 is going to increase. There is an anomalous one. Aluminum is anomalous because when we remove an electron, we get a full filled state for our s orbital, so it actually dips down in energy. And sulfur also dips down just a little bit in energy because removing an electron gives us a half-filled state. So if we remove electron here, you get P3. If you remove electron here, you remove the only P in there, so you get back to a full filled state where you have your S2. So before it was S2P1, then you move that electron, you get just S2, so you have that full filled state, which is a energetically favorable thing. So it's actually not as, it doesn't follow the trend. And of course, as we get larger and larger, our ionization energy is going to go down. So going down a group, our ionization energy also goes down, or it goes down in energy. So going down a group, our I1 decreases. Okay, so our Z effective has a significant part to play. As we have greater Z effective, we will have greater ionization energies. So they will follow along with ionization energies very well. There are some irregularities within ionization energy, and it's usually because of stuff like this where you can get to a full-filled or half-filled state. So you'll see the same thing with boron and gallium that you see with aluminum. You'll see the same thing with oxygen that you see with sulfur. Okay. Last thing we're going to talk about in today's lecture is electron affinity. So this is the energy change accompanied by the addition of an electron to a gaseous atom. And it is almost always exothermic. So instead of requiring energy, it releases energy. Or at least the first one is. The first electron added. Adding an electron to an already negative species is going to require energy. Okay, so there is not significant trends with electron affinity. Generally, as a general thing, as you increase or as you go down or across across your periodic table, you're going to become more negative. So the trend is kind of across the periodic table. The electron affinity becomes increasingly negative. But not always. There's some anomalous things. For instance, nitrogen has a positive value. Group 2A have positive values. So if you have group 2, this has positive electron affinities, EA, electron affinity, because now we're adding into a empty orbital. So we didn't have any electrons in the P subshell, but adding an electron to a group 2 atom will actually cause us to have electrons in that P, so that will be a energetically unfavorable thing. And then nitrogen also has a positive electron affinity, and that's because we have a half-filled state before. By adding an electron, we no longer have a half-filled state. So we have a half-filled D subshell, then an electron was added, and we no longer had that energetically favorable half-filled state. So let me add an electron to an empty subshell. Okay. The last thing I want to talk about real quick is the idea of electronegativity. It's similar in idea to electron affinity. It talks about the desire for electrons, but we call this the measure of the tendency of an atom to attract a bonding pair of electrons towards itself. You can kind of think of this like a tug of war between the two atoms of the bond on the pair of electrons. So if we've got two atoms that are bonded, they're bonded by two electrons, and those electrons, they're an electron density, right? So think about all of our electrons as in terms of like an electron density. If we have a pure equal sharing of electrons, it'll be right in the middle between those two atoms. But if you have one atom that has a greater electronegativity than the other, then you'll actually pull that electron density in a direction. It'll still be bonded, but you're going to pull it in a direction so it'll spend more of its time over in that direction. If you have a great enough difference between those, the electronegativity between the atoms, you actually have the electrons completely transfer to one of the atoms. And this is an ionic bond. So it's we call a pure covalent bond, a polar covalent bond, and then an ionic bond. Okay, so we use the Pauling scale for our electronegativity values. And the values are between 0.7 and 4.0. The greater that number, the more an atom is going to pull electrons of a bond towards itself. Okay? And almost always this trend is going to follow Z effective and atomic size. So our trend, if we think about our periodic table, our Z effective increases like that, as does our electronegativity. We will exclude these. Some of the ones at the bottom have electronegativity values, but we almost always ignore our noble gases when we think about electronegativity because it's talking about the pull of bonding electrons, and our noble gases don't really do much bonding. Okay, so our electronegativity increases with Z effective, and it's going to increase as we go up a group. So our trend is increasing across the group, increasing across the periodic table, increasing as we go up. And that, folks, is everything.